Breathing. It's something we do without even thinking about it. Here on Earth, our planet's wonderful atmosphere gives us all the oxygen we need for free. But when you leave our big blue marble and travel into the vacuum of space, things get a lot more complicated. There is no air out there. None. So for astronauts to live and work in places like the International Space Station or one day on the Moon or Mars, they have to bring their air with them or make it along the way. Think about it. Every breath an astronaut takes is a product of some seriously cool science and engineering. It's a fundamental challenge we must solve to become a truly spacefaring species. Making oxygen in space sounds like something out of a science fiction movie, but it's real, and we've been doing it for years. The most common way is through a process called electrolysis. This is a fancy word for splitting water, H2O, into its basic parts, hydrogen and oxygen. You run an electric current through water, and voila, you get bubbles of hydrogen gas and bubbles of life-giving oxygen gas. The problem isn't making the bubbles. The problem is collecting them. Here on Earth, gravity does the heavy lifting for us. Oxygen bubbles are lighter than water, so they float to the top where they can be easily gathered. It's a simple, elegant system provided by our planet's natural pull. But in the microgravity environment of space, everything floats. There is no up for the bubbles to float to. When you perform electrolysis in orbit, the oxygen bubbles and hydrogen bubbles just kind of hang around in the water, clinging to the electrodes that made them. They create a foamy, bubbly layer that acts like a barrier, slowing down or even stopping the whole process. To get around this, current systems on the space station have to use big, heavy, power-hungry centrifuges. These machines spin very fast to create artificial gravity, which forces the bubbles to separate from the water. It works, but it's not very efficient. This is a huge hurdle for long-duration space missions, like a trip to Mars. Every single kilogram of mass you launch into space costs thousands and thousands of dollars. Big, heavy machines are expensive to launch. They also use a lot of electricity, which is another precious resource that's difficult to generate in space, usually relying on solar panels. Plus, machines with lots of moving parts like pumps and centrifuges can break down. And when you're millions of kilometers from the nearest hardware store, a breakdown can be a very, very big deal. We need a simpler, lighter, and more reliable way to make the air we need to breathe. For decades, space agencies have relied on these bulky, complex systems to generate oxygen. The oxygen generation system on the International Space Station is a modern marvel, but it's a perfect example of the challenges we face. It's about the size of a large washing machine and relies on those spinning centrifuges to separate the gases from the liquid. It's a testament to incredible engineering, but it represents an old way of thinking, one that is constrained by the need to create an artificial version of Earth's gravity. For us to push deeper into the cosmos, for missions to Mars and beyond, we need to think differently. We need to find a way to work with the laws of physics in space, not fight against them. Now consider this. What if we could pull the oxygen bubbles out of the water without any moving parts at all? What if we could just use a simple, fundamental force of nature? That's where magnets come in. It's a beautifully simple idea brought to life by brilliant researchers from places like the University of Warwick in the UK and the University of Colorado Boulder in the US. They asked a very clever question. Can we use magnetism to solve our bubble problem? It turns out oxygen is weakly magnetic. The scientific term is paramagnetic, but all you need to know is that a magnet can attract it, just not as strongly as it attracts an iron paperclip. This new method is a game changer because of its sheer simplicity. Instead of a big spinning machine, imagine simply putting tiny magnets, or micromagnets, into the electrolysis system. As the electricity splits the water, the newly formed oxygen bubbles are gently but firmly pulled away from the electrodes by the magnetic field. They are drawn through the water to a collection point, leaving the electrode surface clear and ready to make more oxygen. There are no pumps, no centrifuges, and no complex moving parts that can wear out or break. It's an elegant solution that uses a basic property of matter to do all the work for us, quietly and efficiently. The beauty of this magnetic separation technique is that it requires no extra energy. The magnets themselves, often made from a material called neodymium, provide the force for free. They create a passive system that continuously and automatically separates the gas from the liquid. This drastically reduces the power requirements for an oxygen generation system, freeing up that precious electrical energy for other critical tasks, like running scientific experiments or powering communication systems. It also dramatically reduces the weight and complexity of the hardware, which is the golden ticket for designing future spacecraft and habitats on other worlds. It's a radical shift from mechanical force to magnetic finesse. An idea is one thing, but science is all about testing it. So the international research team got to work. They needed to see if their magnetic concept would work in a real microgravity environment. To do this, they took their experiment to a special facility in Germany called the Bremen Drop Tower. This amazing structure is exactly what it sounds like, a very tall tower that lets you drop things. Inside a capsule, an experiment can experience about 9 seconds of near-perfect weightlessness as it falls. It's a fantastic way to simulate the conditions of space right here on Earth, without the huge expense of launching a rocket for every single test. During these drop tower experiments, the team ran their electrolysis system with and without the magnets. The results were, in a word, spectacular. Without the magnets, they saw exactly what you'd expect in microgravity. The oxygen bubbles just stayed put, smothering the electrode and slowing the whole process down. But when they activated the magnetic field, it was like magic. The oxygen bubbles were immediately and efficiently pulled away from the surface where they were being created. The video from the experiments is incredible to watch. You can literally see the bubbles being guided and collected by an invisible force, clearing the way for more oxygen to be produced continuously. The data backed up what their eyes were telling them. The team measured the amount of oxygen they could collect over time, and the numbers were astounding. The magnetic system showed a 240% improvement in the rate of oxygen collection compared to the system without magnets in the same microgravity conditions. That's not just a small tweak, that is a massive leap forward in efficiency. It means you could potentially produce the same amount of oxygen with a much smaller and lighter system, or get more than double the oxygen out of a system of the same size. These tests proved that the principle wasn't just a theory, it was a practical and powerful solution. This collaborative effort between different universities and research centers highlights the best of science. By combining expertise in chemistry, physics, and engineering, the team was able to take a fundamental scientific property, the paramagnetism of oxygen, and turn it into a practical technology that could change the future of human space exploration. The successful tests in the drop tower are a critical step toward developing a flight-ready system that could one day be used on the International Space Station, the Artemis moon missions, or the first human expeditions to the surface of Mars. It's a brilliant example of how science builds upon itself to solve big problems. So, what does all this mean for the future? It means that staying in space for a long time just got a lot more feasible. For missions to the moon or Mars, which will last for months or even years, we can't just pack all the oxygen we need like it's a suitcase. It would be far too heavy and take up too much space. We have to be able to live off the land, a concept known as in situ resource utilization, or ISRU. This means using resources we find at our destination, like water ice that we know exists on both the moon and Mars. A lightweight, efficient, and reliable oxygen generator is the key to unlocking that potential. Imagine a future Martian habitat. Astronauts could mine frozen water from beneath the Martian soil. They would then melt it and feed it into an electrolysis system. Using this new magnetic technology, the system would hum along quietly, using minimal power from solar panels to split that Martian water into hydrogen and breathable oxygen. The oxygen would fill the habitat, providing a safe, Earth-like atmosphere for the crew to live and work in. The hydrogen could even be combined with carbon dioxide from the Martian atmosphere to create methane, which can be used as rocket fuel for the journey home. This technology is a critical piece of that puzzle. This discovery is exciting because it ripples outward, affecting so many aspects of space exploration. Lighter life support systems mean we can pack more scientific instruments, more supplies, or even more astronauts on a single mission. Lower power requirements mean habitats can be supported by smaller solar arrays, making them easier to build and maintain. Higher reliability from systems with no moving parts means astronauts are safer and more self-sufficient, which is absolutely vital when you're 200 million kilometers from home. This isn't just about making a better machine, it's about making long-term human presence beyond Earth a practical reality. It's about taking the next giant leap. Ultimately, this innovation is profoundly inspiring. It shows us that sometimes the most elegant solutions to our biggest challenges are found by looking at the world, or in this case, the universe, in a new way. By understanding a fundamental property of a single oxygen molecule, we can design systems that will allow us to breathe on another planet. It's a powerful reminder that the universe is full of amazing properties just waiting to be discovered and harnessed by curious minds. As we continue to explore, to ask questions, and to experiment, we will find more of these keys that will unlock the cosmos for all of us. The future is out there, and thanks to science, we'll have the air to breathe it in,